Dear students, in this session we are going to discuss about set transform. We know that we have gone through the Laplace transforms, and basically these Laplace transforms are used for the analysis of continuous time signals and systems. And now here we are discussing about discrete time systems. In the case of discrete time systems, usually set transforms are used for the analysis purposes. So, let us see the set transform. So, the set transform is used for the frequency domain analysis of the discrete time systems. Basically, the discrete time systems are represented by f of k, and the set transform of that discrete time signal f of k is represented by f of z, that is f of z is equal to z of f of k. So, the set transform of a discrete time signal is defined as f of z equal to sigma k equal to minus infinity to plus infinity f of k into z raised to minus k. And here z represents a complex variable. Here from the equation you can see that k equal to minus infinity to plus infinity. That means it have a negative side and positive side. So, we can say it as a two-sided set transform. That is, time index k is defined for both positive and negative values. Similarly, we can define the one-sided transform of f of k, and in that case there will be only one side will be there, either positive or negative. So, here f of z equal to k sigma k equal to 0 to infinity f of k into z raised to minus k. So, this is the basic form of the set transform equation, and in our discussion we are mainly concentrating on the one-sided transform, set transform. So, we will be using this equation. So, for doing problems to find the set transform, a formula, that is geometric series sum formula, will be useful for you, and it is given as sigma k equal to 0 to infinity c raised to k will have a form 1 by 1 minus c, where c is a constant. So, if this formula comes in your equation, you can replace this with 1 by 1 minus c. So, remember this one, this will be useful for doing problems. So, now we can go through the properties of the one-sided set transform, and this also will help you to solve the problems in a simple manner. There are some properties like linearity property, and here we are discussing about discrete time signals, and there are two signals f1 of k and f2 of k, then the corresponding set transform are f1 of z and f2 of z. So, we can suppose if there is a signal f of k and its set transform is f of z, then first property, see linearity property, that means discrete sequences are f1 of k and f2 of k, then a1 into f1 of k plus a2 into f2 of k will be equal to a1 into f1 of z plus a2 into f2 of z, that is a set transform property. That means this linear combination will be equal to the linear combination of set transforms. And next is the shifting property. Here m greater than or equal to 0. That means if f is shifted by f of k plus m, similarly f is shifted by f of k minus m, then corresponding set transforms will have the form. For this, suppose f of k has a set transform f of z, then f of k plus m set transform will be z raised to m f of z minus sigma I equal to 0 to m minus n f of I into z raised to m minus I. So, this is in the case of shifting to f of k plus m. Similarly, if there is a shift of f of k minus m, then the set transform will be z raised to minus m into f of z. Next is multiplication by k. Suppose if we are multiplying the signal f of k by k raised to m, then the corresponding change will be in the set transform is there will be differentiation comes in the set transform pair, that is k raised to m into f of k results into minus z d by dz all raised to m f of z. That means f of k has the set transform f of z, but if there is a form k raised to m comes along with this f of k, then the corresponding term is minus z d by dz of all raised to m into f of z. Next is scaling in z domain or multiplication by a raised to k, that is a raised to k into f of k will have the form in set transform as f of a inverse z. So you should remember all these formulas. You can apply this in doing the problems. Next property is time reversal, that is f of minus k will results into the set transform as f of z inverse. Conjugation is f conjugate of k will results into f conjugate of z conjugate. Convolution property is multiplication will results into the product of the set transform pairs, that is sigma m equal to 0 to k h of k minus m into r of m will results into product of this individual set transform, that is h of z into r of z. Next is there is theorems, initial value theorem and final value theorem in the case of set transform, that is f of 0, that is initial value will be equal to limit z tends to infinity f of z. Similarly, final value theorem says that f of infinity will be equal to limit z tends to 1 minus z inverse into f of z. That can be written as limit z tends to 1 z minus 1 into f of z. These are the main properties of the set transform. Let us do a problem. It is a simple problem to find the set transform of f of k equal to 1 by 2 all raised to k into u of k. So here u of k means unit step function. We can define u of k as u of k will be equal to 1 for k greater than or equal to 0 and it equal to 0 for k less than or equal to 0. That means here the signal has value 1 only between the interval 0 to infinity. So we can take the set transform equation as a set transform. We know that f of z will be equal to sigma k equal to minus infinity to plus infinity f of k into z raised to minus k. That is the formula. And here instead of f of k we can substitute this, and here its speciality is that u of k equal to 1 between 0 to infinity. Okay. So we can rearrange the equation of set transform as z of f of k equal to f of z, that is equal to sigma k equal to minus infinity to plus infinity f of k into z raised to minus k. Here the limit will changes from 0 to infinity since we are using u of k. That will be equal to 1 by 2 all raised to k into z raised to minus k. Here instead of u of k we are using 1, okay, because it is a unit step function. This can be written as sigma k equal to 0 to infinity. Here k is common, so we can take it outside. So 1 by 2 into z raised to minus 1 all raised to k. So we can use geometric series sum expansion formula because it is in the form of 0 raised to k. So it can be replaced by 1 by 1 minus c. Here c, instead of c we are using 1 by 2 z inverse. So we can write f of z will be 1 by 1 minus c. Okay. This will be equal to sigma k equal to 0 to infinity c raised to k is equal to 1 by 1 minus c. That is the geometric sum series formula. So that can be applied here. So we will be getting f of z equal to 1 by 1 minus 1 by 2 z inverse. So that will be equal to, if we are multiplying and rearranging this, we will be getting 2z by 2z minus 1. So you can do the problem by using this geometric sum series formula. Okay. Next we have another f of t sin omega t. Let us find the z transform of this sin omega t. Here we can write f of k equal to sin omega t, f of t equal to sin omega t, and it's a discrete. This is a continuous time signal. Usually z transform is used for the frequency domain analysis of the discrete time signal. So we have to discretize this signal. So let this discrete time signal is obtained by replacing t by kt, where t is the sampling period. So we can write it f of k will be equal to sin omega kt. Okay. So we can write a set transform of f of k equal to f of z, that is equal to sigma k equal to 0 to infinity f of k into z raised to minus k. See, here we are discussed about one sided set transform, that is why we are using the limit k equal to 0 to infinity. Okay. Instead of f of k we can write this term, okay, sin omega kt into z raised to minus k. We know that sin theta has a form e raised to j theta minus e raised to minus j theta by 2j. Similarly, cos theta has a form e raised to j theta plus e raised to minus j theta by 2j. That is the divided by 2. That is the formula for sin theta and cos theta. Okay. See, cos theta is e raised to j theta plus e raised to minus j theta by 2. So here we are using sin theta, that is a question. So we can, instead of theta you can substitute omega kt. Okay, right. So f of z will be equal to sigma k equal to 0 to infinity. Instead of e raised to j theta we can write omega kt minus, you can just substitute for theta. Okay, you will be getting this equation. Here you can separate the terms by multiplying with z raised to minus k. So you will be getting 1 by 2j into sigma k equal to 0 to infinity e raised to j omega kt into z raised to minus k minus 1 by 2j into sigma k equal to 0 to infinity e raised to minus j omega kt into z raised to minus k. So here we are using, see here is a term, this term, okay. You have this term, so set transform of this term, that is the meaning of this equation, right? Set transform of this term, here f of k is this one, so that will be equal to, we can write sigma k equal to infinity e raised to plus or minus akt into z raised to minus k. That will have the form z by z minus e raised to plus or minus at. See, this is obtained by using the geometric sum series formula. That is, in the case of c raised to k, we have the formula 1 by 1 minus c. Here instead of c, we are having e raised to plus or minus ak e raised to at z inverse. That is c. So we can obtain z by z minus e raised to plus or minus at, right? So that we have used in the previous case also. Here also we are using the geometric sum series formula. Similarly, we can apply the geometric sum series formula in this case also. So this and this term will become in this form, okay. So we will be getting f of z equal to 1 by 2j z by z minus e raised to j omega t minus 1 by 2j z by z minus e raised to minus j omega t. That is obtained by applying the geometric sum series formula. See, here we are replacing this actually it was 1 by 1 minus c formula, but here in the case of c there is an inverse term comes, that is why we are getting z by z minus term, okay. So here we can cross multiply this equation, so we will be getting z into this term, that is equal to z minus e raised to minus j omega t minus z into this term, okay, divided by 2j into z minus ej omega t into this term. And here we can multiply the terms inside the bracket and we can cancel the similar terms, so you will be getting this equation. So finally we can write f of z from this equation, we can write it z into sin omega t. See, this is the case like sin omega t, so we can write z into sin omega t divided by z square minus 2z cos omega t plus 1. Here when you reached here, you can directly write this equation by using the properties of the set transform. See, we have some common formula for one side set transform. If you are by hearting these formulas, then you can easily solve the problems. So these are the some results. Here f one side we are calculating the one sided set transform. Here f of k or f of kt is given, that is if it is delta k, then the set transform is 1. If it is unit step function u of k, then the set transform is z by z minus 1. If it is a raised to k, then set transform is z by z minus a. If it is k into a raised to k, then the set transform is az by z minus a all square. If it instead of k, here k square comes, then it will be like az into z plus a divided by z minus a all cube. So there are different formulas like this. You can go through this common formula and you can apply this directly to the equations in the problems, okay. So try to go through this one, or else you can find these formulas by substituting instead of f of t, and you can find it in the regular manner. So these are the results of set transform for some common formula. Here you can see in the table sin omega kt is there. We have derived its equation as you can see in this problem we have derived the equation. So you can either go in this manner or you can directly write this equation for complicated problems, okay. Directly from this table you can write the equations for doing complicated problems, okay. So try to understand this results. That's all about this topic. Thank you.